Hey everyone, welcome back to Trigonometry. This will be lecture 6 of the course. And in this section, we're going to shift gears slightly and begin talking about the graphs of the sine and the cosine function. So let's go ahead and jump into it. This will be lecture 6, graphs of the sine and cosine function. So we'll be graphing sine and cosine in the xy plane. And so as a result, we're going to want to switch slightly to the notation that we're used to when graphing things in the xy plane. So we'll be using this notation, y equals f of x, which in this case will be sine of x, or y equals f of x, which is cosine of x. Now this is just a convention, when we're talking about graphs in the xy plane, we want to typically use the variables x and y rather than theta or gamma or phi or something like that. So in these instances, x is going to be the angle measured in radians, and we'll stick with radians for this lecture, though I may toss in the degree equivalent from time to time when I think it might be necessary. So we'll start with the sine function. Start with this one. And so we'll start with some values of the sine function that we know of. Okay, and so if I have x and I have the sine of x. All right, so let's say I know, let's start out with a little bit of detail here just so we can remember what's going on here. Pi over 6, pi over 4, pi over 3, pi over 2. Now, we can just simply look up these values if we want to. We've got our unit circle right here, and we can just look at the values of the sine function. So it starts at 0, and then goes to 1/2, square root of 2 over 2, square root of 3 over 2, and then 1. Okay, and so we can just drop those on here. So it starts at 0, and I don't have that on the actual. I think I want that there, though. Let's put a 0 here. So at 0, it is 0. Okay, at pi over 6, we said it was 1/2. At pi over 4, it's the square root of 2 over 2. And then it's the square root of 3 over 2. And then at pi over 2, it tops out at 1. Okay, and so this is what it looks like in the first quadrant. And now we'll kind of increase the resolution here, and we'll jump up to pi, and then to 3 pi over 2, and then up to 2 pi. Now what does it do here? Well, it goes from 1, and then it drops back down to 0 when it gets around the circle, and then it drops all the way down to -1 at the bottom of the circle, and then it comes back to 0, right? So starts at 0, and it drives up to 1, and then it comes back down to 0 over here, right? In the same manner in which it increased. So it increases from 1/2 square root of 2 over 2, square root of 3 over 2, and then it decreases square root of 3 over 2, square root of 2 over 2, 1/2 down to 0, right? So it has the same descent as it does increase, and that'll be important when we actually try to draw it. And then it drops down to -1 at the bottom, and then it comes back to 0, and then it just starts over, and it keeps going around like that, infinite, for whatever degree, whatever angle beyond 360 that you're interested in, right? So it kind of follows this pattern. Okay, so let's just see what this looks like when we plot it on a coordinate system, right? So let's take this to be, of course, our x component, and then this will be y equals sine of x. Okay, and so the points we want to plot are 0, 0, right? And then pi over 6, comma 1/2, and then pi over 4, comma square root of 2 over 2, right? And so on, right? We want to plot all these points. So I'm going to try to do a nice plot here, something that looks reasonable. Okay, so I'll see 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Okay, so this is 0, 0, and then this I'm going to make pi over 2, and then I'm going to make this pi, and then 3 pi over 2, and then 2 pi. Right, and obviously we could keep going around if we wanted to. Okay, so here it's 0, and then let's make this 1 and then -1. Okay, so at pi over 2, it's equal to 1, so it comes all the way up to here. Now remember, it's got kind of this smooth ascent, right? So it kind of comes up like this. Not quite like that, actually, about like that. Okay. Right, and so this point, this point, this point, this would be like your pi over 6, your pi over 4, your pi over 3. Right, and so you can see pi over 4 pi over 6 is roughly here, and that's supposed to correspond to 1/2, roughly. Okay, so it kind of comes up like this, and then it's going to come back down and cut through 0, and then it's going to be over here, and it's going to come down to -1, and then it's going to come back up to 0. And of course it keeps going like this, right? It just keeps doing this. Okay, and this is the sine function. Okay, so this is y equals sine of x. And this curve, this characteristic curve that you see here, you've certainly seen things like this before. This is called a sinusoidal curve. Sinusoidal, right? So it's got this characteristic shape. Okay, and it just keeps going like this to infinity, right? It looks like this all the way to, as large of an angle as you want, and then also in the opposite direction, right? If you're going backwards on the circle, the angles would be negative, and it goes in the opposite direction in the same manner. Okay, now something to notice here is that you have a period right here. So the period here is the portion of the curve where the sine does the unique stuff, and then it just starts to repeat itself. So what you can think of it as is this section here could just be, you could just copy it over to here, and it's going to look exactly the same. And then you could copy it further over, right, and just look exactly the same, right? It just keeps doing this same thing, to infinity. It never stops, right? It keeps going. And it's got the same exact pattern, the same slopes, the same everything. Okay. So this is what the sine function looks like when it's plotted on the xy coordinate. And remember, this is just the most basic sine function that you can have. Y equals sine of x. No, nothing fancy here. Okay. Let's talk about some of the properties of the sine function. Some of these things we will have hit on in earlier lectures, but let's give it a little more thorough treatment here. Not super thorough, but a little bit. So properties of y equals sine of x. Okay, so the domain of the sine function is -infinity to +infinity. All real numbers. Right? You can put any old number you want in there as long as it's a real number, meaning we can't put square root of -1 in there. We can't put complex numbers in like imaginary numbers. That's kind of the main issue there, right? So all real numbers. What about the range? Well, we just saw that the range goes from -1 up to +1, right? Right? We saw that it starts out, it's -1, it starts at 0, then it goes up to 1, and then it goes down to 0 again, and then down to -1, and then it turns back around and comes up again. So that's the range. Now we saw that the sine is an odd function. Right? We talked about this previously, and what that means is that the sine of -x equals negative sine of x. Okay, and this will come up. This will be important when we start plotting some of these. We just said that the period is 2 pi, meaning it starts to repeat itself after 2 pi radians, right? So whatever the value is right now, 2 pi radians from now, it'll have the same exact value. Okay, and it'll continue on like that. And at 2 pi radians after that, it'll have the same value again. And then 2 pi after that, it'll have the same value again, so on. Okay, Now the x-intercepts, I don't know if this is super important, but I'm just going to list them. So obviously we know that it's 0 at 0. It also is equal to 0 at pi, 2 pi, 3 pi, right? Basically every pi interval, right? And so it goes the other direction as well, negative pi, negative 2 pi, and so on. Right? That's where the x-axis, that's where the sine function bottoms out. All right, so remember it starts here, that's the 0, goes up to pi over 2, and then it comes back down, and that's pi. Then it goes down to 3 pi over 2, and then it comes back up, and that's 2 pi. Right? And then it does it again, 3 pi, and does it again, 4 pi. Okay, so that's what we mean by the x-intercepts everywhere it crosses the x-axis. Now, how many times does it cross the x-axis? Infinitely many times. It does it infinitely many times in both directions. And yeah, I think we'll leave it at that. Right, so the x-intercepts, and this just gives you a sense for kind of what it looks like and some of the key properties here. Remember, any real number can be plugged into the sine function. It's always defined for all real numbers, right? So remember some of the other ones like tangent and some of the cosecant, secant functions, they have limitations on their domain, but sine function's everything, works everywhere. Okay. And remember, we're only talking about the basic sine function here, so the range will change when the function changes, and we'll see examples of that in a moment. The period can also change when the function changes, and we'll see examples of that in a moment. Okay, let's do an example where we try to plot this thing, right? And so to make it a little more interesting, let's try to graph y equals 3 sine of x. Okay, so this is an example where we're going to change the way the graph looks a little bit. It's still going to have the basic characteristic here, but it's going to be stretched a bit. All right, and so the domain doesn't change. Nothing changes here in the domain. It's negative infinity to positive infinity. Now the range is actually different. So normally the range would be from -1 to 1. So -1 up to +1. Now, but if you think about it, like if I hide the 3 here, the range is going to be -1 to 1. But what's going to happen here is that whatever sine is equal to, whatever sine of x is equal to, it's going to get multiplied by 3. So that means it bottoms out now, instead of at -1, it's going to bottom out at 3 times -1. And it's going to top out at 3 times +1. Right? So that means the range is now changed to -3 up to 3. So it's like we've taken this thing here and we're stretching it. It's going to be stretched out further, right? So normally it would only go to there, but now it's getting stretched further. Okay, and that's the effect that this 3 has on it. It stretches it vertically. So the 3 here is actually called the amplitude. So in this case, 3 is called the amplitude. It's called the amplitude of the function, right? And we'll come back to this in a moment, right? But just to make this example a little more interesting, we want to throw a little something else on it. Otherwise, we're literally drawing the same picture that we did on the previous page, right? And so we can think of our sine function as, you know, this is 1, 2, 3, and it's going to occupy the same basic space. I'm going to start at 0. Here's pi over 2. There's pi, 3 pi over 2, 2 pi. And instead of going up to 1 only, it's going to jump up to 3. And then it's going to come back down to 0. And then it's going to go down to -3. And that's going to come back up to 0. And of course, it keeps going like that in both directions. Okay, so important to note here, this is the point pi over 2, comma 3. This is pi, comma 0. This is 3 pi over 2, comma -3. Of course, this is 2 pi, comma 0. And this is 0, 0. right? So there's the points, right? So we've just graphed this sine function with this special amplitude. Right? So it's got this coefficient on the front that kind of stretches it. Okay, all right, so that's the sine function, introduction to the sine function. Let's take a look next at the cosine function. Okay, we'll run this in pretty much the same manner. So the cosine function. So for the cosine, we're going to start again with our x values. So we've got 0, pi over 2, pi, 3 pi over 2, and 2 pi. Okay. And let's put the sine functions on here just for comparison. So sine, remember, it starts at 0, then it goes up to 1, and then it comes back to 0, then it goes to -1, and then it goes back to 0. Okay, so that's a whole period of the sine function. Now what about the cosine? Cosine's not the same as sine, is it? Well, you can look at the unit circle and you can see that it's different. Obviously everywhere it's different. Well, a couple places it's the same. Right? They do intersect at points. Right, but you can see like the sine starts at 0, the cosine starts at 1. And then at pi over 2, sine is 1, cosine is 0. Right? And so they vary a little bit. So we start at 1, and then it goes down to 0, and then it goes down further to -1, back up to 0, back up to 1. That's what the cosine does. So let's draw the cosine. So I've got my 0, and then pi over 2, and then pi, 3 pi over 2, and 2 pi. So remember, the cosine starts up here at 1. So it starts up at the top. Remember, sine started down here. Cosine starts up at the top, and then it goes down to 0, and then it goes down to -1. And then it comes back up to 0, and then back up to +1. So this is the cosine function. Right, and then I'll just sketch in the sine function behind this so that you can just see how they compare. Right, so the sine function looks like this. Right, so this is y equals sine of x, and this is y equals cosine of x. Okay, so you can see the difference there. Right, it's like it's shifted, isn't it? Right, if you can think about it like this, if I take the cosine function and I just shift it over, right, I can make it align with the sine function. I can make it lie right on top of it. I just have to add pi over 2. I have to phase shift it forward. And we won't talk about phase shift in this section, but it is a thing. And we can make them back to it in later sections. We're going to start with just period and amplitude, though. What are the properties of the cosine function? Again, the base cosine function. Well, the domain, again, is all real numbers. Right? Cosine's another function that we can plug anything into. No restrictions. The range. We just saw that the range is -1 up to 1, just like the sine function. They're the same. Domain and range are the same here. Now, a cosine is an even function. Cosine is an even function, and that means that the cosine of -x is equal to the cosine of just x. Okay. The period here is 2 pi again, right? You can see that in this picture, right? It starts to repeat itself, right? It runs from 1 all the way to 2 pi, and then it starts to repeat itself. It's going to come back down. This section right here of the cosine is going to look exactly the same as this section. Right? It's going to go down and then back up, just like it does here. Okay, so it has the same period as the sine function. And then let's talk about the x-intercepts real quick. Right, so we can see that the cosine intercepts at pi over 2, 3 pi over 2. right? So we're going to have a pi over 2 intercept and a 3 pi over 2. And you can imagine what the pattern would be here. It'd be 5 pi over 2, 7 pi over 2, etc. Okay. And in the negative direction, you would have a 0. Sorry, no, not 0. It would be negative pi over 2. And then it would be negative 3 pi over 2. All right, that's where all the zeros are at. So those are the x-intercepts. Okay. All right, and so yeah, you can kind of see on here, like if this is going to come back down, it's going to cross here, which would be negative pi over 2, right? So it's pi over 2, negative pi over 2. Right, and it's just going to repeat this same pattern on the negative axis. Okay, so that's where you get all your x-intercepts. All right, let's graph one of these. Let's do an example. Okay, let's graph one. Let's say we want to graph y equals 2 times the cosine of x. Okay, so just like with the sine example, this is going to have the range is going to be changed by the fact that by this 2, this amplitude value up front here. So normally the range is equal to -1 to 1, but now we're going to be multiplying it by 2. Right, so instead it's going to be -2 to 2. Okay, other than that, this is a straightforward cosine function, right? So it's almost like you can just draw a cosine function and then label the y-axis differently if you like. Right, so it's going to start out high, and then it's going to come down, then it's going to go down further, then it's going to come back up, and then it's going to go back to the top. Right, so it'll look like this. And let's label this +2 up here, and then -2 here. Right, so this would be the point 0, 2. This would be the point pi over 2, 0. This would be pi, -2. This guy here would be 3 pi over 2, 0. Right, and then up here, this is going to be 2 pi, 2. Okay. All right, so that is the cosine function. Okay, all right, let's dig into this idea of amplitude and period a little bit further. All right, so our goal will be to plot things like, things like y equals 10 sine of 2 pi x over 3, for example. Right, so this kind of a function here is going to have a amplitude piece and a period piece. So there's going to be an adjustment to how tall the sine function is in this case, and an adjustment to how quickly it oscillates, and so the length of the period. Right, and so in general, the functions we'll be interested in are going to look like this: y equals a sine of omega x. Right, and this thing here is going to tell us the amplitude that we've already seen. We'll talk about it a little in more detail in a second here. And this is going to tell us something about the period. It informs the period. Right, it's used to determine what the period of the graph is. Okay, and so we'll start with the amplitude. Okay, so the amplitude is going to be equal to the absolute value of whatever a is. Okay, it's the absolute value, meaning if a is like -5, then the absolute value of a is 5. If a is 10, then the absolute value of a is 10, right? So it basically takes whatever the number is and makes it positive. And the amplitude tells you how much the sine function is stretched or compressed vertically. It tells you how much the function is stretched, and stretched whenever a is greater than 1, or compressed whenever a is less than 1. Okay, and here I mean the absolute value of a. Right, so if a is like 1/2, then it's going to be compressed. The graph will be shrunk down. Its max will be like 1/2 instead of 1. Right, and if a is 1,000, then it's going to be stretched very, very, very far. It'll be much taller than a normal sine function. That's the idea with the amplitude. Okay, that's the idea. Let's just draw a little picture to help this be clear. Help this look clear in our heads, right? So let's take a sine function, and let's say the sine function, here's 1 and -1. So it starts at 0, and I'll just kind of make it a little smaller here. So it starts at 0, and then it comes up to here, comes down to there, down further, and then back to 0. So it kind of goes like this, right? This is a sine function normally. Well, if I increase the amplitude, then it's going to jump up higher and go down lower, right? So maybe it comes up like this, and then comes down like that, and then like that. Right, and so let's say that goes up to 2 and maybe down to -2. So this guy here, the really dark one, the darker of the two, this is like y equals 2 sine of x. Right, and then this one is the normal one, y equals sine of x. Now, we could also make the amplitude do something else. We can make it go like this. Right, kind of have a shallower valleys and shorter peaks, right? And this would be like, this guy here would be like y equals 1/2 sine of x, right? So you can see how the amplitude is just going to stretch it vertically, right? Now notice the amplitude doesn't do anything to the period. The period is constant for all 3 of these. Right? So the amplitude has nothing to do with the period. It only has to do with how much the stretches affect the vertical orientation of the thing. Okay. All right. So that's the amplitude. Right? We saw a couple of examples of that already. It's very straightforward, the amplitude. Easy to visualize, easy to work with. Let's talk next about the period. Okay, so the period. Now the period, as I said, shows up here in the sine and cosine functions as a factor inside the argument. All right, so here the omega is inside the argument. We call this the argument, like whatever you're plugging into the function. All right, so in this case, the factor that influences the period is found inside the argument of the sine function. Okay. So normally, the period, which we'll denote as t, is equal to 2 pi for sine and cosine. Right, we've seen that already. Normally, the period is 2 pi for sine and cosine. But if you have a factor in here that's different than 1, right? So if you see a factor written inside the argument of the sine or cosine function, then that means the period is being affected. Okay, so in the case of something like this, the period is going to be equal to, we'll call it t, and it's going to be whatever the function's period normally is, in the case of sine and cosine, 2 pi, and it's going to be divided by whatever this factor omega is. Okay, now what does the period tell you about the graph? Right, this is how we could figure out what the period is. What does it actually tell you? Well, what it tells you is it gives you some indication about how much the graph is stretched. But this time it's how much it's stretched horizontally. Right? So the period tells you, well, we know what the period tells us is how long, how far does the graph go before it starts to repeat itself, right? But when we're dealing with a function that has a different period, what it's really informing you about is the graph stretched out more, and is it stretched out horizontally more? The period tells you how much the function is stretched or compressed horizontally. Right, this time horizontally. Before it was the amplitude, it was vertical stretching and compressing. Now it's horizontal, right? So normally, let's think about it like this. Normally the sine function looks like this. Kind of goes like this. This is normal. That's what we're used to. Now, if the period is decreased, then what you'll end up seeing is a sine function that does something like this. Right? So the period went from out here to this new graph here, where now the period is half as long as it previously was. So in this case, if this is y equals sine of x, then this is y equals sine of 2x. So this one is y equals sine of 2x. And let's see, why is that? Well, the period is equal to 2 pi over omega. In this case, omega is 2. So it'd be 2 pi over 2. So now the period is shrunk down to pi. And that's what we're seeing here. This would be 0. This would be 0. Pi over 2. Pi. Right? So the period shrunk down to pi in this case. Right? And it'll just keep doing this. Right? So it'll, in the time that it takes for the original sine function to do one period, this sine function will do 2 repetitions. Right? It'll go through 2 periods in the same amount of time as the original sine function goes through 1. Okay. All right. Very good. Very good. Let's. That's the idea of the period. Let's do an example where we find the period and the amplitude. Okay, so let's, we want to be able to pull these values out of here easily. So let's find the amplitude and the period for y equals -3 sine of 4x. Okay, so the amplitude is the absolute value of a, which is in this case absolute value of -3, so 3. That's the amplitude. And what is the period? The period is equal to, in this case it's a sine function, so the normal period is 2 pi. We have to divide it by the omega, and so I get 2 pi over 4, and so pi over 2. So this one is really shrunk down, isn't it? This one is going to complete 4 revolutions, 4 periods in the same time as it takes to complete 1 period normally. Right? So as this number here gets larger, then you should think of the, if this is the normal sine function, as it starts to get larger, it gets closer. If it gets really large, then the sine function is right on top of itself. It just gets really, really compressed horizontally. Right? Now, if this is a really small fraction, then the normal sine function will look like this. And if it's a really small fraction for the period, it'll stretch it out. Right? It'll start to stretch it out so that it takes longer to complete a period. All right. Okay, that's amplitude and period. Now let's talk about a general procedure for graphing these things. Like when we start throwing in lots of different variations, we need some kind of a method that's easy to remember, easy to apply, and gets good results, like you know, across the board here. So we're going to use what's called the key points method, and it capitalizes heavily on the fact that the graphs of the sine and the cosine, they have a particular shape, right? And when you're talking about graphs of cosine and sine that are only vary in terms of their period and their amplitude, then the shape is retained at all times. It's just going to be stretched in one direction or the other. Okay, and so here's the general method. So this is going to apply to functions of the form y equals a sine of omega x, or y equals a cosine of omega x. Right, now there is a third variation that can be plugged into the sine and cosine function. That's called the phase shift. We're not going to get into the phase shift in this section. We may come back to it though. Okay, so step one here is we need to find the amplitude and the period for the function. So find the amplitude a and the period, which we call t, we denote with a t, for the function. That's step one. You need that information. You need to know how much it's being stretched before you start trying to figure out the values and where to plot it. How much is it being stretched, and in what direction is it being stretched? Okay, that's step one. Step two. Step two is we need to once we know the period, we need to divide the period into some intervals. Okay, so we need to divide the interval 0 up to the end of the period, which would be 2 pi over omega. That's t. We need to divide this interval into 4 subintervals. Right, so you can just think of that as like this. So I've got, you know, this is my 0 up to 2 pi over omega. I need to break it in half, and then I need to break it into fourths. So I've got 1, 2, 3, 4. Okay, so this is like my 0, and this is my 2 pi over omega. Right, now the key points are going to take place at these cutoffs. So these are the key points. These guys here. Right, so by this step you'll already know the two ending key points, the first key point and the last key point. The middle three are easy to find. You just break the interval in half, and you know this one, and then you break this interval in half and you forgot that one, and you break this interval in half and you got that one. So step 3 then is to use the cutoffs to find the 5 key points. Need to find those 5 key points. All right. And then really the last step is to it's kind of we'll make it 2 steps. So once you have the 5 key points, identify the value of the function at the 5 key points. And identify the value of the function at the 5 key points, and then finally plot the points, plot the 5 points, and draw a line through them. And this is trig, right? These are smooth lines. Draw a smooth line between them. Okay. All right. So this is the method. First, you start by finding the amplitude and the period. You then divide. Once you know the period, you know the interval where the graph is doing something unique, and you divide that interval into 4 subintervals. 1, 2, 3, 4. And these subintervals are going to define the 5 key points. 1, 2, 3, 4, 5 of them. Right? So you use the cutoff, step 3, to find those 5 key points. We'll do an example in a second. You'll see this is pretty straightforward. Once you've got the 5 key points, you basically plug them into the function to identify the value of the function at the 5 key points. We'll do an example in a sec. That'll be clear. And then you just plot those 5 points, and you draw a smooth line between them. It's just that easy. Okay. And again, this capitalizes on the fact that everything that happens between key point 1 and key point 2 is well known. It just is going to be a nice smooth curve up, right? Unless it goes down, in which case the amplitude will tell us that. And then it's going to come back around, and then it's going to go back up, and then it's going to come back down, right? So the idea is that the sine function kind of looks a particular way across here. So I just need to know where this peak is, I need to know where this valley is, and I need to know where it comes back, right? That's the point of these intervals. Okay, let's try an example. Let's do an example. We'll be very explicit. We'll stick to this method on this example. All right, so let's graph y equals 2 times the sine of negative pi over 2 x. Step 1. Let's identify the period and the amplitude. Amplitude is really easy. It's just going to be the absolute value of a. In this case, that's the absolute value of 2, which is just 2. So we've got the amplitude. The period is going to be equal to this t, which we say is 2 pi over omega. And so you have to be a little careful here. So this is 2 pi over omega, and now omega is negative pi over 2. Okay, so make sure you're careful when you're doing your arithmetic here. Right now, I'll be very deliberate here. 2 pi is the same as 2 pi over 1, and negative pi over 2 in the bottom like this, right? So I got a fraction divided by a fraction. Remember to invert the denominator and multiply. So 2 pi over 1 times 2 over negative pi, like so, right? And so then you just simplify, do the multiplication and simplify, and so I would get 4 pi over negative pi. Well, this is just negative 4. Okay, so the period in this case comes up as negative 4. Okay, so what that basically means is, what this means is that a cycle is going to begin at 0 and ends, in this case, at negative 4. Now, what that really means, because we're talking about the sine function, what that means is that the fact that it's negative tells you that the graph is going to go in the opposite direction. Right, so normally the sine function would look like this. It would start low and it would go up like this, right? This is normal. What we're dealing with is something like this. It's going to start at 0. Instead of going up, it's going to first go down. It's going to look like this, right? And so that's the idea here. That's the idea. That's what's going on here. Right, and so you can kind of think of this as, instead of ending at negative 4, we know that it could go this direction or it could go this direction. Right, let's just make this a positive 4 and say that our period goes from 0 up to positive 4. Okay. All right. The negative just tells us, because the sine function is an odd function, so sine of negative x equals negative sine of x. Right? The negative is what causes it to change directions here, right? And so that's what we're being informed of when we come across that. Okay, so that's step 1. We got the period, we got the amplitude. Okay, step 2. We need to know these intervals, right? And so this one is very easy. It goes from 0 to 4 radians, and so the interval is very easy to see. Right? It starts at 0 and it ends at 4. Well, what's the midway point? Well, that's 2. What's midway between 2 and 4? Well, that's 3. This would be 1. Right? So our 5 key points are, our 5 key x values are 0, 1, 2, 3, and 4. Right? It couldn't be easier. Okay? So those are our 5 key points. So now what we need to do, step 3, is to use the cutoffs to find the 5 key values, right? Okay, so that's actually what we've done here. We had the interval 0 to 4, we broke it in half and got 0 to 2, we broke that in half, 0 to 1, and then broke 2 to 4 in half and got to 0.3. Okay. And so what we want to do in step 3, let me make sure I'm following the steps just right. Use the cutoffs to find the 5 key points. Okay, step 4 then is to identify the value of the function at the 5 key points. All right, so this is actually step 3. Step 2 was identifying that it goes from 0 up to 4. Right, and then it breaks down into these intervals. So really, step 2 and 3 are kind of the same, aren't they? Right? You're really just kind of looking for these intervals. So maybe it didn't need to be broken apart. But okay, so step 4 then is to find the values of the function. So let's see what happens when we plug in x equals 0, for example. I'm going to steal a little bit of extra notebook space here. Well, I think I'll just switch it over. I don't want this to get too messy. Right, so this will be step 4. So x equals 0. We plug that in. What do we get? Well, remember the function is y equals 2 times the sine of negative pi over 2, and in this case times 0. Right, and so that is 2 times the sine of 0, which is 0, right? Sine of 0 is 0. Right, so our first point is 0, 0. Next, let's plug in x equals 1. So y equals 2 times the sine of negative pi over 2 times 1. And so that's equal to 2 times the sine of negative pi over 2. Okay, and what is sine at negative pi over 2? Well, it's negative 1. And so that would be negative 1. So in this case, it's 2 times negative 1. So it's equal to negative 2. And so the second point is 1 comma negative 2. All right, then what happens at x equals 2? Well, there we have y equals 2 times the sine of negative pi over 2 times 2. And so that is 2 times the sine of negative pi. And that is equal to 2 times the sine of negative pi is 0. So that's 0. So our third point is 2 comma 0. I bet you can guess what our third point will be. Okay, so that's y equals 2 times the sine of negative pi over 2 times 3. So that's 2 times the sine of negative 3 pi over 2. So that's 2 times 1. Okay, which is equal to 2, right? And so here I've got the fourth point is 3 comma 2. And we'll just do the last one. So that's y equals 2 times the sine of negative pi over 2 times 4, which is 2 times the sine of negative 2 pi. And of course, that's equal to 2 times 0. So this point is 4 comma 0. Okay, that's a 4, not a y. It looks like a y. That's 4 comma 0. So you can see it goes from 0 up to down to negative 2, as we said it would, back up to 0, up to 2, back down to 0. All right, can we plot this thing? You betcha. You betcha. All right, so there's 1, 2, 3, and 4 radians. Right, of course, 0 radians is here at the beginning. And so it's 0, 0. That's the first point to plot. And then 1, negative 2. So 1, and then we'll make this negative 2. And then 2, 0 is here. And then 3, 2 is up here. And then back down to 0. So it goes like this, just like we kind of said it would. Now notice that this one does go down before it goes up. That's the result of the sine being an odd function. So sine of negative x equals negative sine of x, right? So this fact that the sine is, the negative argument makes the whole function negative, right? You can see that in the way our function is set up here. 2 times the sine of negative pi over 2 times x. Negative pi over 2, so the argument's always negative. Well, it's negative when you plug in a positive value anyways. And so that's what's going to cause it to flip upside down here and to go down instead of going up first. So normally it goes up, right? Right, so this one is just flipped. Okay, perfect. All right. Excellent. Okay, so I think that is a great place to end it. Well, let's do one more example, actually. One more example. This is an example where we're given the plot, we're given the graph, and our job is to figure out what the equation for the graph might look like. Right, so let's say our example, is that focused there? Let's make this a little better. Okay, so let's say our job is to find an equation for the following graph. Okay, so let's try to get a decent drawing here. Okay, and so this will be 1 and -2, -3, 1, 2, and then 3 will be up there. Okay, so let's say it starts here, and I'm going to make my points here. This is going to be 1, 2, 3, 4, and then 5. And let's say it comes down to -2, and then comes back up, and then goes up to +2, and then comes back down, and then ends up down here again. Right, so this one goes like this. Okay, so our job then is to figure out what equation should we use. First thing to ask yourself is this a cosine or a sine function? And really, like, because we're not dealing in phase shifts at all, that's as simple as asking, like, does it start at 0 or does it start at the top or bottom? It starts at 0, right? So first of all, it looks like a sine function. Because it starts at 0. 0, 0, let's say, right? It has a value of 0 at 0. Right, so that tells us that we're dealing with y equals a sine of omega x. Right, now something to notice here is that it does flip downward. Right, it does drop down instead of going up. So that means our amplitude is negative, or possibly the argument omega is negative, since sine is odd. It's usually best to think about the function, the curve going down instead of up, as being an amplitude issue. Right, there's always a way to write it as an amplitude issue instead of a period issue. Okay, now let's talk about the period. That's next, right? So the period, it looks like it goes from up to 4. Okay, the period is 4, and the amplitude we can see is equal to 2. Okay, so let's start with the amplitude. It's a little easier to negotiate amplitude stuff. Right, so the amplitude, which we can see it's 2, right? Right, and we know that that's equal to the absolute value of whatever a happens to be. And the fact that it goes down first tells me that a should be equal to -2. Okay, the negative is going to flip the sine function upside down, and it's not going to impact the amplitude because the amplitude is equal to the absolute value. So now our graph, our equation must be y equals -2 times the sine of omega x. Okay, so the last thing to figure out is, what is this omega? Well, the period is 4 instead of 2 pi, right? So the period is stretched some. So let's see what it looks like. So for the period, the way you want to think about this is, you know what the period is equal to, right? And you know what the period of the sine function starts out to be. So it's 2 pi over omega is equal to 4. Right, that's what you need to figure out. You need to figure out what omega is. Right, this is just an algebra problem, isn't it? We can just solve for omega. Right, we can just do a little bit of algebra here, and we can namely divide both sides by 4 and then multiply both sides by omega. And so you get omega is equal to 2 pi over 4, which is pi over 2. Okay, So omega equals pi over 2. And that tells me the final piece of information that I need. I just need to know what that omega is. So now the equation is y equals negative 2 sine of pi over 2 times x. Right? And I think if you go through the process in reverse and you try to graph this function, you'll see indeed it's exactly as we've said. It is exactly this image here. Okay. All right. I think that is a great place to leave it. So in the next lecture we'll get together, we'll talk about graphing additional trig functions like tangent, cotangent, secant, cosecant. They all are they're connected somewhat to what sine and cosine are doing. Tangent, cotangent are a little weird, but the other ones are very connected. All right, so we'll leave it there, and we'll talk to you all later. Take care.